Hello everyone, and welcome to the next lecture in my deep learning series. This lecture is about manifold learning for time series or dynamical data. In the last lecture, we have started manifold learning and we have discussed principal component analysis, a linear shallow learning method, and autoencoders, a deep learning method. Both methods attempt to minimize the reconstruction error that occurs when you compress the data to a low dimensional latent space and then lift it back to the full dimensional space. And it turns out that at least for PCA, minimizing the reconstruction error is equivalent to maximizing the variance of the data in the latent space. So there is an equivalence between different loss functions. In this lecture, we will consider time-lagged data. So for example, pairs of data points at the current and the next time step of a time series. And again, we will consider to minimize the error of predicting the next time step from the current one while going through a low dimensional latent space. And we will see there is again another equivalent optimization objective, namely to look for the latent space representation that best resolves the slow processes or the rare events. So we are looking for the slow manifold of dynamical data in this lecture. We will also consider shallow learning methods, for example, the time-lagged canonical correlation analysis, TCCA, and the time-lagged independent component analysis, TICA, as well as deep learning methods, time autoencoders and WAMP-nets, for example. Finally, it's important to understand that the methods we are considering in this lecture are Markovian. So we always want to predict the next time step from the current one. We are not considering previous history, so this is a restriction. And with this restriction, we cannot hope to do an optimal job in time series prediction. And that is not the objective of the current lecture. Our objective is to learn a low-dimensional manifold that is still easy to interpret. So that means you can go from any full-dimensional state to a latent state and back. And you have a simple dynamical model after learning that governs the time evolution. A Markovian model, such as a Markov chain. And that has a lot of advantages for the analysis. If the objective is, however, to predict the time series as long as possible with as little error as possible, then it is better to include memory into the model, into the learning problem. And that is something we will discuss in the next lecture on recurrent neural networks. Okay, so we have a plan. Let's get started. Enjoy the lecture.